Multiple choice, ask multiple choice, part 1. Okay, these are questions that you could see and probably will see on the multiple choice section of the AP Stats test. So let's go over the content. Okay, so for the first one, let's look at confidence intervals. So for confidence interval, before we do this one, let's look at this. For a confidence interval, remember the confidence interval is within here, within some sort of, let's say, negative A and positive A, or something like that, some value A and B, we could even say, let's say A and B. And if HO is in the interval, it is a fail to reject because there's nothing abnormal. We do not have enough evidence for HA, and our results are not statistically significant. However, if it is outside the interval, either higher or lower, we reject HO, we have enough evidence for HA, and our results are statistically significant. So either if it's higher or lower. So let's go ahead and look here, and we see 40,000 is outside the interval because it's less than both of these numbers. And so therefore, this is what I kind of make I gave myself a little note sheet. Since I'm rejecting HO, that means I have evidence for HA, and that is significant. So then when I read through these things, I'm able to figure out which one I know. So I'm looking at saying, is this statistical significant? That's what it is. Could this be information to say against the alternative hypothesis at this level of significance? So it's asking if I'm going to have significance, and since I am outside the interval, I'm going to say yes, it is going to be in favor. So I'm not going to say this one. And when we look at the difference, this one says would be, and this one said would not be. But remember, reject HO, have evidence, it is significant. So that's why it's D. Now make sure you take time to stop and do the problems. Even you're going to have to put mine on pause. I know I'm going to be talking very fast. So the next one here is conclusion for p-value. So let's jump over here. Before we do this one, I have a little thing I want to show you. So if I give you, like on this one, it says, here's the test statistic, and then here's the p-value. Well, this one's given, but what if I don't give you the p-value? Can you find the p-value if you just know the test statistic? So I want to jump up here and show you how to do that. So let's say I'm given the test statistic t equals 1.2 with a degrees of freedom of 9. Okay, so if my HA is less than, my p-value I'm going to find with using TCDF. Lower bound is negative infinity because it's this over here. Upper bound is 1.2 because that's my test statistic. Degrees of freedom is 9 because that's what was given to me. And my p-value is going to get me as 0.87. If it was a HA greater than, same thing, except I'm going to use TCDF again because it's a T test statistic, except this time the lower bound is going to be 1.2. Upper bound is going to be my infinity, and the degrees of freedom is given to me at 9. And my p-value is going to be 0.13. For a not equal to, I'm just going to do one side, which I already did, found the p-value at 0.13, and I'm going to double it because it's both of those. Okay, if I'm given a test statistic of a z equals 1.2, we're going to do the same thing I just showed you above, except with normal CDF and not TCDF. Same thing with chi-squared. If I'm given a chi-squared, it would be a chi-squared CDF. All right, so that's how you, given a test statistic, can find a p-value. So all it is this area under the curve. Okay, so let's go to this one here and check this out. Now remember, I'm looking here, the p-value of this one is low, and it's pretty low, and is it lower than this alpha? Yes, so that would be reject HO, convincing evidence for HA. Convincing evidence for HA, I read through here and I say, okay, this says, is there convincing evidence to the data that distribution has changed? So is it different? And that's what this says, is different. And so yes, this is the true answer. I'm going to go ahead and read through the other problems because just in case, sometimes the questions are really, really close and the answers are close and you misread it, and the reading a correct answer alerts you to that. So I'm going to go ahead and see what the problem is for this one. This is true. It is lower than this, but it says do not. And remember, P low, reject HO. it does provide convincing evidence. So reject ho, convincing evidence for ha, significance. The mean number of customers randomly is 12.5. So what they're asking, we're wanting to see if this is particularly true or not. And if we add all these up and divide by 4, we get 12.5. However, it's not proportional because this is 25% of the time, 20% of the time, 30% of the time. So if you use it with proportion, it's not going to be 12.5. No valid conclusion can be made because the observed frequency of one cell is less than 5. Now be careful. This sounds like it is a condition for chi-squared, but remember, it's not a condition for chi-squared observed, it's expected. So make sure you write that down, that your expected cells for chi-squared has to be cannot be less than 5, have to be greater than or equal to 5. Not observed. Chi-squared statistic, it says 51 minus 49 is degrees of freedom. That's not correct. It's 4 minus 1 because it's 1, 2, 3, 4 categories. Minus 1 is 3. Okay, so conclusion based on p-value. When I look at this, immediately I see this as a chi-squared because I have 2 variables and I've got one here and one here, and so I've got all of my values in here. So I see it gives me a p-value of 0.001, and that's a low p-value. It's going to be reject no matter what alpha I have because it's pretty low. So I went ahead and wrote notes on my paper, reject ho, convincing evidence for ha, statistically significant. And when I see this, it tells me I'm testing to see if instant replay is independent. So ho, independent, remember whatever the name is. So ho, independence, which means no association, ha, not independent. All right, if this were a homogeneity test, which it's not, it would be ho would be the homogeneity test. So what I'm trying to say is make sure that your ho is the test that you're running. That's important because in a second you'll see. The number of degrees of freedom is 8 minus 1 is 7. No, for a chi-squared 2-way test, it's row minus 1 times column minus 1, which is going to be 4 minus 1 times 2 minus 1, which is clearly not 7. Chi-squared test should not have been used because 2 of the counts are less than 5. Again, 2 of the counts, this is not these, it's expected counts that I have to watch out for. The null hypothesis states there's an association between category and opinion. An association, that's what ho says. No, ho says independence or no association. Small p-value suggests there is evidence of an association. Small p-value, because we have a small p-value. Reject ho, convincing evidence, statistical significance. So yes, it is. So yes, this is the correct one. Okay, for analyzing bar graphs, two things I just want to point out to you. Right here, I wrote on the right. You only can compare counts or numbers within a category. Meaning, because what if I have 1 million of brand X, 1,000 of brand Y, and 100 of brand Z? The fact remains that I don't know how much I have of either of them. But if I had 1 million of brand X, even this would be more than any of the other ones. So, but because I do not know how many I have in each, I cannot compare how many I have in this one versus this one. So, the second thing to note is the only way you can do is percentages if you only can compare percentages from one category to another category. So for this one here, for the last three, you can see all 3 of these go from X to Z. And you're going to see, okay, I have more in this bag versus this bag. So therefore, I can't compare those two because I don't know how much are in there. So these are the only 2 that I could actually look at, and B is the only correct answer because there are more in the red versus the green. For this one here, same idea, and it's D. Okay, for choosing the test, let's kind of look at how to choose a test. I've got a little note of how to choose the test here. Okay, so the first thing for you to do is to determine if it's proportion or if it's means. If it's proportion, it's going to be Z or chi-squared. And of course, if it's means, it's going to be T. So if it's proportion, you have two choices. You've got one population or two populations. Let's just look at the one population. If my one population has one sample and I'm comparing that one sample to the population, it's a one prop Z test. Let me give you an example. An example would be like if I said red M&Ms have 25% of the bag are red M&Ms, and I see does that relate to the other ones? But is how accurate is it from the population? So for versus a one population, I could have several categories like this one, a chi-squared goodness of fit. I have red M&Ms, maybe I have 25 of these, and I have 30 of these, and I have 15 of these, and I have 40 of these, something like this. So is it proportional if this is 25% and this is 15% and this is 10%? Is it proportional to what my population to be? This is very similar to the one prop Z test, except it has several categories. And this is a chi-squared goodness of fit. Okay, if it's one population but I have two variables being compared, that's a chi-squared independence, and I'm trying to say, for instance, this is grade level and job choice. Remember when you were in second grade and asked what you wanted to be? What proportion of people want to be firefighters, police officers, astronauts, jobs like that, in different grade levels? Maybe we'll try third grade and versus seventh grade, and then let's say versus 12th graders, and see if it's independent, if the age is independent from the job choice. Okay, if it's two populations and I've got two samples being compared, for instance, the proportion of red Skittles, do I have more proportion of red Skittles to the proportion of red M&Ms? If it's two populations and I have this, and it's asking the same, and I've got one variable, and I'm saying, okay, let's say I have Manville, I have Pearland High School, and I have Dawson High School, and I'm asking again what college choice do they have? Are they going to go to U of H? Are they going to go to Rice? Are they going to go to UT? Are they going to go to Alvin? What college choice are they going to do? What's the population? Are they the same? Is Manville's proportion equal to Dawson's proportions equal to Pearland's proportion? And you could do two of them, or you could do more of them. Those would be a homogeneic test, where I'm seeing if the proportion of those are the same. Okay, let's check out means. For means, for one population, one sample being compared to the population, this would be maybe the number of detentions on average that we have in 2020, let's say 2024, and we're comparing the 2024 detentions to the historic average. Okay. Sample a paired T if I have each subject or pair gets paired with both treatments. So for instance, if I have like a before-after treatment where you're getting some sort of a medication, and I get both treatments, and I measure my blood pressure before, I measure my blood pressure after, and see if the medication had a difference on me. One population with two variables is going to be a least squared regression line, and that's pretty easy to tell because you've got two quantitative variables, or it's got data output, or it's got a line, but you're going to be looking for two quantitative variables that you are able to graph a line to. And the last one is the two population is the two sample t-test, and the two sample t-test gives me where I have one thing, maybe I'm talking about an average number of detentions like we talked about before, but detentions maybe in 2024 versus in 1980, and see if the average number of detentions at a certain school has increased, decreased, or just not the same. Okay, so now what I'd like you to do is I'd like you to make sure that you put these on pause for a second, and then you go ahead and try these and see if you get the right answer. I'm not going to pause at all, so you have to put the video on pause. So the fact that I see proportion, I know it's not a T, I know it's not a T, I know it's not a T, because proportion has to be this one, but I'm talking about two things, so it has to be a two sample t-test. Okay, sorry, I think I missed some. I did. Okay, so for this one here, for number 20, again, I can get rid of, because it's proportion, I can get rid of everything that is not proportion related. But then I noticed it's very similar to, like, I would write ho, p is equal to 0.15, ha, p is greater than 0.15. And so this lines up to one proportion comparing to the population. For this one here, we have means, and you can see that I have two separate samples, the employees, them, so immediately I can get rid of the Z's, and I can get rid of the one sample because I see I have two samples, so I know it's either a paired or a two sample T. But I know it's a two sample T because let's say Randy is in sample 1. He is not connected to anyone in sample 2. There's no connection in sample 2. And remember, each group, to be a paired, each pair or subject has to receive both treatments. All right? And in this case, it's just a group of independent people here is in 1, and independent people here has treatment 2. The only thing that they have in common is that they work at the same factory, but they didn't pair them together in any unique way. All right, for this one, this is an obvious chi-squared. Either it's a chi-squared two-way test which is either independent or homogeneic, because you see a matrix here, and you see you've got two things it's talking about, and I've compared them. And so the chi-squared two-way test, since it only gave me independence, I know that's what it is. The goodness of fit would be something like where it just gives me observed values. It might give you your expected values, but I'm only talking about one thing. It would be like if it looked like this, if it had men like this, and then had boom, 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 that could be a chi-squared goodness of fit. But the fact that I have men and women means that it cannot be. It has to be the independence or the homogeneic. Okay, so for this one here, the first thing that I did is I noticed that it was a quantitative variable. It was looking for time, so I canceled out these bottom 3 because those are not. Those were all for proportion. So I know that it's either match paired or t-test. The reason I settled on match paired was because each woman got both treatments. And so she's matched with herself. Okay, last thing I'm going to talk about is minimum sample size. And for minimum sample size, this here is the equation, is the mean is equal to z star times s over square root of n. This is for means. Now, notice I don't have t star, I have z star. And the reason I'm using z star instead of t star is because I don't know n. In order to find t star, I have to have a degrees of freedom, and I need n to find degrees of freedom. So that's why I have to use what I've done. So we're going to go ahead and put this in. For margin of error, I have 5, and then for the z star, I have 1.645. The way I got that is this, because I'm asking for a 90% confidence interval. Remember, I have to put in 0.95 into my inverse norm. So I put in area 0.95, mean standard deviation 0 and 1, and that's where I get the 1.645 from. The standard deviation is 35, and that's where I get this, and this is square root of n. And then I just do my math, and I end up getting n is equal to 32.6, but I need to make sure I round up. Always round up for n, because if I think about this, if this is rounded down, this makes it smaller, which makes this larger, which makes this whole thing larger, and which means I don't stay within the 5. And then I pop out, I'm a little bit higher than the 5, I'm like 5.1. And so therefore I round up because I make this larger, which then makes the whole side on the right side, it makes it a little smaller, so I don't make above the 5. So, but you always round up. No matter what you have, it's round up. Okay, so for this one, for minimum sample size for proportion, it's margin of error equals z star p hat q hat over n. And if you do not know p, if p hat is unknown, use p hat equal to 0.5. And of course, q hat equals to 0.5. And the reason being is because that's what we call a worst case standard deviation, because it's the biggest standard deviation I can get out of when p plus q is equal to 1. The biggest product of pq is going to be 0.5 times 0.5. So that's why we use it as a worst case scenario. So you're going to put margin of error, this one here, 0.02, equals z star, which is 1.96, which of course you can go to inverse norm of 0.975 for the area, and then 0 and 1, because you have to do the 95% plus the tail. And then I don't know p, so I put 0.5, and over n. Okay, you're going to get n equals 2401. And so you're going to go to the next one higher, which is 2,500. Okay, and this last one here, same thing, is that margin of error equals z star, and it's means, and so it's s over square root of n. And so I'm going to find this 99.6% by putting 0.998 in there, and that comes out to be about 2.87. And s is going to be 0.3 because it's right here. Margin of error is 0.12, and square root of n. Okay, and for this you get 51 point something, but it doesn't matter, you go up to 52. Okay, thank you for listening, and I hope this helps.